Okay, so now we've got the concept of double integrals, and we also have the connection between double integrals and symbolic integration. It's time to now look at double integrals over general regions. And well, let's just take a look at a simple example. If I asked you to integrate the function f of xy equals xy squared over the triangle with vertices 0, 0, 1, 0, and 0, 1, then technically speaking, because we have not defined yet what these integrals would be, the answer would be, well, okay, so let's take a look at the definition. The definition is, well, you take a function that is defined on a two-dimensional region D that is not a rectangle. And if we want to integrate that thing over that region, we basically pick a rectangle AB cross CD that contains the region D. And then we set the function capital F of x to be f of xy for xy in the region D and 0 for x not in the region D. So this is very similar to what I mentioned when we talked about integrating over objects that are not boxes. You would just set the density function equal to 0 on the outside. Similarly here, we just simply set the height function for the two-dimensional function for the function of two variables equal to 0 outside the region that we're interested in. And then we simply define the double integral of the function over the region to be the double integral of the newly defined auxiliary function capital F of x over the rectangle that contains the region. Well, that's great, and that's the formal definition. And that works whenever the right-hand side exists, which is another formal can of worms that we're not going to go into. But basically, so now the answer is not the answer now is, how is that going to help? Because this is a purely formal definition, and certainly this is something because there is a pretty deep theory behind the whole thing that must be respected, that tells us that it makes sense that we should do that, not to mention that it tells you a standard technique to model all sorts of objects, which is we simply set whatever function we have equal to 0 outside the object. We still need to figure out how to compute those integrals. And so actually, if we go back to the same example, we still want to integrate the function f of xy equals xy squared over the triangle with vertices 0, 0, 1, 0, and 0, 1. We're basically left to some visualization skills, and well, we've practiced visualization. So how hard can it be to visualize a triangle? Well, here's an x-axis, here's a y-axis, here's the point 0, 0, here's the point 1, 0, and here's the point 0, 1. Well, the triangle is this red triangle here, and what we can see is that in the x direction we go from 0 to 1, and in the y direction, well, in the y direction we don't go from 0 to 1 also, because that would give us a square, right? The square 0, 1, 0, 1. But in the y direction, we start at y equals 0 and end at y equals 1 minus x. So basically what we have is, as we march across the x-axis, we integrate from 0 to 1 minus x going up. And that's typically how I'm going to indicate these integrals. There are various ways of associating verbiage with these integrals, but really the idea is you've got to see the picture. And just as in the presentation on Fubini's theorem, the arrows will always tell us from where to where the inner integral goes. All right, so that means our integral over this triangle of xy squared dA is the integral from 0 to 1 in x, the integral from 0 to 1 minus x in y of the integrand xy squared, and then dy dx, where of course now our variables or our differentials and our integral signs again act like parentheses. And the rest is just computation, because whether the inner integral has a variable upper bound or not does not matter. We solve it the same way, right? So let's now do the computation. This is the integral from 0 to 1 of x times the antiderivative of y squared with respect to y, so that would be 1/3 y cubed. We take that in the bounds from 0 to 1 minus x, where y goes from 0 to 1 minus x, right? Because dx is still here. And yeah, so y equals 0 gives us that there's nothing to be subtracted, so this is just the integral from, is 1/3, take the 1/3 out, integral 0 to 1, x times y being 1 minus x, so 1 minus x cubed, and then dx from here. So that's just a straight plugging in. Now we have some algebra. Well, we have to multiply out these parentheses. And so as we do that, we would get negative x quantity cubed, which is negative x cubed, times x gives us negative x to the fourth. Then we would get plus 3x squared times x, which gives us plus 3x cubed. And you can see how this keeps going. The next one would be minus 3x, and then times x gives us minus 3x squared. And finally, we have plus 1, which gives us, when we multiply by x, gives us plus x. Okay, antiderivative of that. Okay, look, it's tedious, right? We're getting a lengthy polynomial, but nonetheless, it is still just a polynomial. And so the antiderivative for that will be the 1/3 will stay out front. We get negative 1/5 x to the 5th plus 3/4 x to the 4th minus x cubed plus 1/2 x squared, right? Yeah, negative 1/5 x to the 5th plus 3/4 x to the 4th minus x cubed plus 1/2 x squared from 0 to 1. Okay, so the lower bound again does not contribute anything, and at 1 we just have to add all those fractions up. Common denominator is 20. So let's see, negative 1/5 is negative 4/20. 3/4 is 15/20. Minus 4/20 is 11/20. 11/20. Hang on, there's something that doesn't want to agree with me right now. Okay, so let's see. Negative 4/20 plus 15/20 is negative 11/20. Is 11/20, yes. Minus 20/20 is negative 9/20. Plus 10/20 is 1/20. And that's indeed the 1/3 times 1/20 that we have here. So the answer is 1/60, and that is it already. And this example already shows everything that we need to know about the idea of integrating double integrals over general regions. And that is, we need to draw the region and then decide whether we want to have our integral to go in the y direction or in the x direction, and then we just simply set up the integral. And I'm not going to associate verbiage with that. I'm just going to show you the two ways in which this can be done. Namely, to set up double integrals, well, we want to visualize and draw the region, or slash draw the region. We need to decide which integral to make the inner or outer integral, and then we set up the integral, and the rest is just computation, as we have seen previously. The computations themselves were not that bad. They can get more and more tedious. You can have fractions involved and all sorts of other horrible things, but in the end, we know how to solve integrals, so the rest really is just computation. If we want to look at that specifically with an inner integral being dy, basically when you draw the region, and I'm really practicing what I'm preaching here, you really want to draw the region, visualize the region. And if your region is so that you've got a lower function, which is a function of x, function b of x, a lower bound, a bottom, and another bound that is the top function of x, like that, well, if your region then is bounded like that, then of course what you want to do is you want to have that your outer integral goes from a left bound to a right bound, and your inner integral is the dy, where you go from the bottom to the top, right? Because if I were to make my inner integral an x integral, I would have to go from the left bound to here, then somehow skip some stuff, and then go from here all the way to the end. So things would get very, very complicated also, because then all of a sudden here I could go all the way across. Whereas if my setup is like it is here, then I know I can always go from the bottom function to the top function in a straight line, which very much suggests that your inner integral should be an inner integral dy. And I think there are then, in calculus texts, there are authors well-meaningly calling these things regions of type 1, regions of type 2, and all that. Look, nobody cares what type that is. You need to see the picture, and once you've got the picture, you need to be able to turn the picture into the integral. And of course, once you have this picture, you realize, hey, my outer integral goes from the left to the right, my inner integral goes from bottom of x to top of x, my integrand is whatever it is, and then my inner integral is dy, because I'm going up in my inner integral, and my outer integral is dx, and that is the whole setup. Similarly, if my inner integral turns out to be dx, well, that's actually something that you find out after the fact, because first you would want to draw the picture in an xy coordinate system, and if your function is, or if your bounds are so that you've got a left bound that is a function of y, and a right bound that is a function of y, and your region is what's in between those things, again, it would be unnatural to try to integrate in y first, because you would have an integral that is even interrupted here. Whereas if you first integrate in x, you just go straight across in the various lines that I typically said I would put in there. And so y would go from bottom to top, and then x would go from left to right. And your setup would be that your integral goes from bottom to top, inner integral goes from left to right, where left and right both depend on y. Integrand is whatever it is. Inner integral is dx, outer integral is dy. And again, it's the picture that tells you what the integral is, and once you know what the integral is, you set up the formula. You don't need a piece of vocabulary that says that this is a region of type A, region of type B, region of type 1, region of type 2. You need to see the picture, digest the picture, and turn it into an integral. What we then can do with that is, well, we have already seen that, for example, for the triangular region, we could have set that up either way and things would have worked out. But every so often it's actually beneficial to interchange the order, which I think is what we're going to do next. No, first we've got some helpful hints. Some helpful hints is you want to make sure that the bounds of the outer integral are numbers or constants, right? Because the outer integral cannot have bounds that depend on integration variables. You want to make sure that the bounds of the inner integral only depend on the integration variable of the outer integral. They cannot depend in particular on the integration variable of the inner integral. These are things that ultimately will come very natural, and you may already be insulted in me telling you things that look quite obvious to you, and if they do, congratulations. Basically, the idea is here we're slowly getting used to, one more time, to working with integrals that have variable bounds, and so there are just certain things that can't happen, right? The bounds of an integral cannot depend on the integration variable, cannot depend on the dummy variable. And then the big one really is after you have set up the integral. After you have set up the integral, think about the region one more time to make sure, think about the region that is encoded by the bounds in the integral. And that is just to make sure that you really still have the same region. And if that region does not look as specified, you've got to double check your setup because something is not happening. All right, so now we're going to talk about interchanging the order. And so here's an example. We want to compute the integral from 0 to 2, and the inner integral goes from x squared to 4 of e to the y squared x dy dx. Okay, so you look at that and you realize, hey, I can take the y out. That's great. That makes the inner integral easier, hopefully. Well, it doesn't. Or, well, it makes it easier, but the inner integral is horrible because the function e to the y squared is one of those functions for which we don't have any decent antiderivatives, right? Or no antiderivative in closed form. All right, so maybe if we delay the dy integration and first do the dx integration, we get something that will allow us to make a substitution. However, in order to get to that point, we first have to visualize the region of integration. So we draw ourselves a coordinate system, and if necessary, you really put the scale on there, and if necessary, you really plot points. Well, you don't necessarily have to do that here, but the key object we're looking at is, of course, the function y equals x squared, and that's this one here. And then that's the lower bound of the integral. The upper bound of the inner integral is y equals 4, so that's a horizontal line right here. And then we realize that the outer integral starts at x equals 2, starts at x equals 0. So it starts here and ends here, which means the region really is just this. And so this branch of the parabola really doesn't contribute anything to the integral. The region over which we integrate is this region that is now marked in red. And the way the integral is set up, we first integrate from, we integrate in the y direction first. So we integrate from x squared to 4, x squared to 4. So this really is what is encoded by this integral. What we want to do is we want to turn that around. We first want to integrate across. Well, when we integrate across, what happens is we start at 0 and we end at y equals x squared. But now the bounds have to be expressed in terms of y. So y equals x squared is not appropriate. Instead, we write this as x equals square root of y, and we don't need a plus minus, because we're only interested in the positive branch of the parabola. So that means this integral actually is being rewritten as now an outer integral in dy, where the outer integral goes from y equals 0 to y equals 4. Okay, here's the integral. It's being rewritten as an integral from 0 to 4. Outer integral is dy. And then an inner integral from 0 to square root of y, like that. And then we have our integrand that we kept, and now the inner integral is dx because we're going across, and our outer integral is dy, and the rest now again really is just computation. Quick double check if we have these bounds. Okay, y goes from 0 to 4, that's right, and x starts at 0 and ends at square root of y. We're still tracing out the same region here. So really this is something where I'm not sure what other colleagues might think of this, because this feels like coloring with crayons to me. It's just that sometimes we can only go across and sometimes we only go vertical, but these arrows tell us exactly from where to where the important inner integral goes, and so I've stuck with this method ever since I first thought of it, or maybe it's another one of those that somebody showed me and I just don't remember. Either way, this is the method I recommend. Here the rest is computation. Well, look, e to the y squared does not depend on x, so I can just integrate and I get that the outer integral stays with us, integral 0 to 4 dy. E to the y squared, of course, is just a constant with respect to an integral in dx, and the antiderivative of x is 1/2 x squared. And if we go from 0 to square root of y, that means at the lower bound we get 0, at the upper bound square root of y quantity squared is y. So we end up with a factor of 1/2, and then we've got the integral of e to the y squared times y. 1/2 integral 0 to 4 e to the y squared times y, just as I said. And now this is nice because this is an integral where we can do a substitution u equals y squared. And here's also one of those places where I would say if you need to review that, go ahead and use paper and pencil. Separately, hit the pause button to work it out. The substitution is u equals y squared. That means du dy is 2y, and then after you do all your substitutions, what you ultimately come out with is an antiderivative of 1/2 y squared. Multiplied with 1/2 gives you 1/4 e to the y squared. Yeah, antiderivative of 1/2 e to the y squared. Multiplied with 1/2 gives you 1/4 e to the y squared in the bounds 0 and 4, and that's just a quarter e to the 16 minus e, I think. Yeah, or e to the 16 minus 1, because e to the 0th is 1. Okay, so that's it. So you can see here that really, no matter what we do, the computation is something that if you're just patient enough, you can work out. And the big key to solving these problems is exactly between the lines, namely exactly between this line and that line. It is in the setup. And no matter what we do, no matter how we want to verbalize that, there is no verbal algorithm that I know of that adequately describes what we're doing here. Because what we're doing is we draw the picture, we analyze the picture, we make a decision, we move on. So now let's take a look at centers of mass. Now the way we did the introduction is that centers of mass certainly are something that is very relevant for three-dimensional objects, and that's also the general formula, but as mentioned there already, you can also work out the center of mass for a two-dimensional object. Think of stuff that is made from sheet metal, for example, and so a problem that says compute the center of mass of a triangle with density function rho of xy equals x, so that the vertices are at 0, 0, 1, 0, and 1, 1. That is perfectly legitimate. That would be something that is made of maybe of sheet metal that gets thicker as we go along. Of course, the way the thickness increases here is quite huge, so that may not be completely realistic. But I mean, we're looking at problems that we can also set up nicely, and I didn't want to put a scaling factor in here, for example. So what would we do? Well, we would do what we always do when we set up integrals, and okay, what we always do, we've just started doing it, but what we always will do, and that is we visualize the object. So here's an xy coordinate system. Here's the point 0, 0, here's the point 1, 0, and here's the point 1, 1. And that means the triangle is this triangle that is marked in red, and if I then want to integrate from 0 to y equals x, that would encode the whole integral over the triangle, with the inner integral being a dy integral from 0 to x. The only other thing I have to remember is the formulas for the mass and for the center of mass. We start with the mass. Well, and the mass is, of course, the double integral of the density against the area, where our density is now mass per area rather than mass per volume. So it's a double integral over this triangle. And the way we set that up would be that x goes from 0 to 1. Y goes from 0 to x, and again, see, we're following the arrows from the lower bound on the inside to the upper bound on the inside. Then we have our integrand, which would be the density, which is a rho. And then we have our inner integral is dy, and our outer integral is dx. And the rest is just computation. I mean, how hard can that integral be? We have, because x is a constant with respect to y, the antiderivative of x with respect to a dy integral is xy, where y goes from 0 to y equals x. That's one of the things we have to be careful with, right? That's potentially a reflex from single variable calculus. The integral of x is 1/2 x squared. Well, if you're integrating against dy, the antiderivative is x times y. So we have to just make sure we keep track of our integration variables. Plug in x, plug in 0, you get the integral of x squared from 0 to 1, and that's of course 1/3 x cubed from 0 to 1, which is 1/3, so the mass is 1/3. The other thing to remember then is the formula for the center of mass, which is 1/m times integral over the object times of density times generic position vector, which in this case is xy, times the area element. In this case, remember, that means we work things out component-wise, and the rest, as long as you can read this formula, the rest really is just computation. And so that means the x-coordinate of the center of mass would be 1 over the mass times the integral over the triangle, density times x dA. And, well, the mass was 1/3, so 1 over the mass is 3. The integral bounds we already know because we're integrating over the same object as before, so we go from 0 to 1 in x, from 0 to x in y, and because the density was x, we have an integrand of x squared. Well, okay, in the same fashion, integral of x squared dy is just x squared times y, and so then from 0 to x, I get that this is x cubed, and then if I integrate x cubed, I get 1/4 x to the 4th, so I get 3 times 1/4 x to the 4th from 0 to 1, which gives me 3/4 as my x-coordinate. And for the y-coordinate, well, same story, only this time I have to multiply the density with y. We get, again, 1/m is 3. Our integral bounds are the same because it's the same object. We integrate x times y dy dx. Okay, so this time we actually get x times 1/2 y squared, right? And so that's 3 times integral 0 to 1 x times 1/2 y squared from 0 to x. Well, that gives us 1/2 x cubed as our integrand. And so then if we pull the 1/2 out, we get 3/2 times integral 0 to 1 x cubed dx. And if I find the antiderivative of x cubed, that's 1/4 x to the 4th. So I get 3/2 times 1/4 x to the 4th from 0 to 1. That's 3/2 times 1/4. And that's 3/8 overall. And that means the center of mass is 3/4, 3/8. And that does make a good bit of sense, because the density is increasing as x increases, and we also have more area in that direction, so the x-coordinate of the center of mass should be very much tilted towards the right end, and the y-coordinate of the center of mass, because the triangle gets thinner as we go up, the y-coordinate should be lower than 1/2, and it is, because it is 3/8. Okay, let's look at volumes. How did we compute areas in a two-dimensional setting? Well, we looked at a two-dimensional coordinate system, and then if we went from a to b and we had a lower function and an upper function, then the area trapped between these two functions was the integral from a to b f of x minus g of x, upper function minus lower function. Well, that ought to work in the same fashion for volumes. So if we look at our typical right-handed three-dimensional coordinate system, we could pick ourselves a domain or a base b. If we then have one function above that, which may be the lower function, and another function above it, which we would call the upper function, then the volume that is trapped between those two should be the following. If b is a two-dimensional region, and lower and upper are two functions so that L is below u on b, then the volume that is bounded below by L and above by u, that volume ought to be v equals integral of u minus L over the base b dA. And the formula for the volume is well and good. Let's now take a look at an example how this is actually implemented. So we're going to compute the volume in the first octant that is bounded above by the plane x plus 2y plus z equals 2. Well, let's see what that looks like. Here's our right-handed xyz three-dimensional coordinate system. We're even going to put scales on the axes here. This is scaled in steps of 1. And now what do we know? On the x-axis, if y is equal to 0 and z is equal to 0, x is equal to 2, which means this point here is on that plane. On the y-axis, if x is equal to 0 and z is equal to 0, well then y is equal to 1. So this point is on the plane. And on the z-axis, when x is equal to 0 and y is equal to 0, z is equal to 2. So this point is on the plane, which means the part of the plane that is in the first octant, and we're really focusing on the first octant here, right? The part of the plane that is in the first octant is this, and that means the volume that we're actually interested in is this pyramid here. Okay, and now certainly there are two ways to do that. One way is to do this with geometry, and we're going to use this as a sanity check, but certainly the purpose of this example is to practice setting up integrals, and so certainly that is what we are also going to do. So first, via geometry, what would we have? The volume of a pyramid is 1/3 base times height. Okay, the height is 2, and the area of the base, well, the base area is a triangle, and the area of a triangle is 1/2 base times height. So the area of this triangle is 1/2 times 2 times 1, so the area of this triangle is 1, and so then 1/3 times base 1 times height 2 would be a volume of 2/3. So that's what the answer should be, and basically what we're then showing here is that the approach towards volumes with integrals is just consistent with what we also do with geometry. And in fact, if I wanted to be completely fair, the way to derive the geometric formula 1/3 base times height is that you do this for a general integral, just as you may have seen in single variable calculus how the formula for the area of a triangle can also be verified through integration. Either way, that would mean we now have to set up an integral here. And so what would the volume be? Well, I would pick as my base this area here, and I don't want to look at the function y equals something depending on x, because I would get a slope 1/2, right? And I don't necessarily like that too much. It would be a whole lot nicer, I would get a slope negative 1/2. It would be a whole lot nicer if x is a function of y, because then I get a slope that is probably an integer. So I'm going to make my outer integral a dy integral, and so y, of course, only runs from 0 to 1. X, however, now runs from y equals 0 to whatever this line is, and this line has x-intercept 2, and then goes down for every 1 across, it goes 2 down. So this line is actually the line 2 minus 2y, and so that means the inner integral goes from y equals 0 to y equals, from x equals 0 to x equals 2 minus 2, from x equals 0 to x equals 2 minus 2y, because when we're going like this, then we're going in x bounds. All right, and then my upper function is, of course, the plane, so my upper function would be z equals 2 minus x minus 2y, and that's indeed what it is. And my lower function, of course, is 0, because the base here is at height 0. Inner integral dx, outer integral dy. Now, make very sure that you understand this setup process, because even though we already know that the answer is 2/3, basically once we hit triple integrals, we will integrate functions across something like that. And when we do that, we will have 3 integrals where the 0 and this thing here are the bounds for the inner integral, and then we have an integrand, and geometry will not give us access to the answer anymore. The rest, however, here is just computation, just like before. So let's take a look at this volume, which is exactly this, and you can already see if I jump to a new panel, it's going to take longer. It's not that it's terribly hard, it's just going to be tedious, right? It's still just polynomial, and in fact, the first thing we do is we simply realize that the 0 is not there, and the antiderivative in y of the antiderivative in x of 2 minus x minus 2y is just 2x minus 1/2 x squared minus 2y times x in the bounds from x equals 0 to x equals 2 minus 2y from up here. Now we just have to plug that in. Again, when I plug in x equals 0, I get 0, 0, and 0, so that's nice. And when I plug in 2 minus 2y, I get stuff that is bad enough, namely, I get 2 times 2 minus 2y from the 2x, I get 1/2 2 minus 2y quantity squared from here, and I get 2 times 2 minus y times y from here. I have an extra equal sign in here. Let's just leave that as is. Okay, I've duplicated an equal sign. Great. How bad can that be? That, I don't think that would even be a deduction if you do that on an exam in my class. Okay, so we move on. Well, now it's algebra. We have to multiply this out, and I think that's actually what I did on the next line. So let's see, 2 times 2 is 4. 2 times -2 is -4y here. Then we've got 2 squared is 4 times -1/2 is -2. 2 times -2y would be -8y divided by 2 would be negative, and with a minus sign would be plus 4y, and then we've got minus 4y squared here, and if you don't want to keep track of all that, here it is, yeah, minus 2y squared. Okay, so let's take a look at this one more time. 2 times 2 gives us the 4. 2 times -2y gives us -4y. 2 squared is 4 times 1/2 gives us 2. 2 times -2y is negative 8y times 1/2 is -4y. 2y quantity squared is 4y squared times 1/2 is 2y squared, and then here we get 2 times 2 times y is minus 4y, and 2 times -2y times y is plus 4y squared. And then we collect, well, 4 minus 2 gives us 2. -4y minus -4y is gone. Minus another 4y gives us minus 4y. And then we have plus 2y squared because we have minus 2y squared plus 4y squared is 2y squared. Antiderivative of that is 2y minus 2y squared plus 2/3 y cubed, right? And that goes from 0 to 1, so we get 2 minus 2 plus 2/3, which is exactly 2/3, and that's, of course, in agreement with the argument that we have just given using geometry. Well, and pretty much that's how you would work out volumes with integrals. We conclude with a couple of theorems, among them being if you've got a region D over which functions can be integrated, then the area of the region is actually the double integral of the function 1 against the area element, and that's basically because if I have a region D, and if I just duplicate that in the z direction with height 1, well, then the volume of this thing, which is what I would compute if I integrate 1 against dA over the region D, the volume of that thing is, of course, area of D times 1, so it is the same number. So every so often, it really does happen that you start out an argument or something by saying that the area of a region is just a double integral of 1 against the area element. Something else then, when you've got two functions that are integrable over the region D, so that f of x is less than or equal than g of x for all points in D, well, then it should be that the integral of f is less than or equal than the integral of g, and that's, of course, because the smaller function traps less volume than the upper function, and that is visually also quite pleasing to see. We take our three-dimensional coordinate system. Here is a function f, which traps this blue volume above the region D. And, well, then if a function g is above f, then, of course, the volume underneath g is the blue volume plus the stuff that is indicated in red here, and that means that this integral is more, the integral over g of g over the domain is more than the integral of f over the domain. And that should be the last one now. Take a function that is integrable over the region D, and let lowercase m and capital M be two numbers, so that the function is literally bounded below by lowercase m and above by uppercase M. Then m times the area of the region D is less than or equal than the double integral of f, which in turn is less than or equal than capital M times the area of D. Here's where we're going to use that lemma about area, because basically what happens is that the inequality m times f of xy, m less than or equal f of xy less than or equal capital M, simply implies that the integral of lowercase m dA is less than or equal than the integral of f, which in turn is less than or equal than the integral of uppercase M dA. And that means, and now for any constant number c, of course, the double integral of c is c times the double integral of 1, and the double integral of 1 we have seen is just the area of the domain, and so this is that this integral is c times a of d, area of D. And so that means we get the implied result, because now this implies the claimed result, because now lowercase m times the area is the double integral of m dA, which is less than or equal than the integral of the function from here, which is less than or equal than capital M, integral of capital M dA, which in turn then is equal to m times the area of D. And that's it. Okay, so we have a couple of results, and I apologize, it's gotten dark outside, and lighting is always something that I am struggling with in these recordings. My wife is sometimes bothered by that, but there's only so much I can do because the overhead lights put too much light on my face here. Either way, that's production value. Okay, what have we seen here? We have seen that the key to all this stuff is the right visualization, which is this mysterious thing that only comes through practice, and we've done plenty of practicing by now, so this ought to work. After that, there is some computation, and we have also seen some theorems about double integrals that ought to work out pretty well for us, because after all, they are visually quite natural as theorems. With that, I leave you to the homework. There is quite a bit of computation there. I want you to also work your way through the computations as much as possible. If it gets too bad, look, set up the double integral, stick it into a computer, see what the computer gives you, but remember, you need to have a certain level of computational skill, and that computational skill is facilitated also by solving some ugly double integrals. With that, I'll see you in the next presentation where we're going to talk about triple integrals. It's the same thing as this one, only one dimension worse. See you there.